Okay. I am Rati Luthani, pursuing PhD from Department of Mathematics at IIT Bombay, and I am a PMRF fellow here. Okay. We will be discussing some questions related to week 1, that is lecture 1 and 2. And I hope the deadline for the first assignment is, like week 1 assignment is 31st August. Am I right?
Yes, ma'am.
Okay. So we'll be discussing just simple questions. Okay. Feel free to ask anything. Just unmute and speak. Okay. Let's start.
Sure.
Okay. Okay. So this is the first question. Consider a finite abelian group G star with elements 1, 2, 3, 4, 5. I think the font is okay. Should I zoom in if you want? I can a
No,
bit.
ma'am, it's okay.
Okay, great. So consider this finite abelian group G, which has 5 elements, and the operation is star. And this operation has been defined with this table. Okay. So you have, so basically for the group, you should know from all of, if you take, okay, if you take any element from like A star B, you should know. That is the thing. So if G star is the group, then you should know for every A comma B belong to G, you should know this A star B. Okay. So this is, then you can always and if that satisfies all the properties, then you have the group. Okay. So right now it is given that this is an abelian group. Okay. So okay, it has been asked that so some entries are not here, like it is not given here. So the question really is, can you find these entries by giving, like if it is given that these entries are here, then can you find the blank spaces? So here it has been asked the second last row of the table, what it will be, that you need to find out. Okay, let's try it if we can do. Okay. Okay. So, okay, as a solution. So, I'm claiming something, then you can always tell me why this is true. Okay, so first thing I'm saying, 1 is the identity element. Can you tell me why this is true? Identity element of G. Okay, first question, why I'm saying the.
Ma'am,
Because
because of
identity element is unique.
Great. Yeah, identity element is unique. So I hope you all know this thing. So I don't need a proof here. So 1 is yeah, that is true. Like we are using the because it is unique. Now I'm saying 1 is the identity element of G. So can you prove it by giving by having these things, like these elements which these things are given? So using this, can you tell me why this is true? This is my claim. 1 is the identity element. This is my claim. Can you tell me why this is true?
ma'am, as we perform any operation, like let's say A star with that identity element will
Yeah.
get the same element,
Right.
like A back again. Yeah. Also, whenever we have a reverse thing, inverse of that same, like A star inverse of A, we will get E. That is the identity.
Right.
And here, E is here the identity element.
Yeah. Right. So, what can you say? So, this is true for every A, right? This is true. So, this is the notation for. Okay, I can write for every. So, for every, if I write like this, I hope you will understand. So, this is a notation for every. So, for every A, this should be true, right? Do you know for every A it is true here?
Yes, ma'am, it should be for
Yeah, it
every
should.
A. And
True, true. Yeah, it should be. Like, yeah, this is from the group, so it should be true. For identity, it should be true. Does one satisfy this property? That is the question.
Ma'am,
Yeah.
ये one is two one is not given, so how can we say one is an identity?
Yeah. I'm not saying it has been proved here. I'm asking, like, I can prove from the given things. So I'm asking you if you can do that or not. Just try. Don't worry about how it will go.
I'm sorry, I didn't get your question.
Okay.
Please, can you repeat?
Yeah, sure. So my question is E is the identity element, no doubt. But why E is equal to 1 here? Why? That is the question. Why identity is equal to 1? Like, there is some identity out of 1, 2, 3, 4, and 5. One of them is identity, no doubt, because this is a group, so identity exists. So which one is it, you need to find out. So my question is, I am saying that 1 is the identity element here. So can you tell me why this is true? Like, it's pretty simple. Just do the math. Don't worry. Like, so okay, I just do that. Okay, so you have 1 star 1 is equal to 1, right? You have this thing, 1 star 1. Now what you
Yes,
can
ma'am.
and just assume, let E be the identity element. Then what you can do, you can write multiply by E, both sides. This is true. So because of this, what you can do, 1 star you have right multiplied by E, both sides. So right multiply. So multiply means we are operating in, like, multiply means we are with the operation. So it's just the, like, easy to say. So we are operating E on this element. So right multiply by E. So what you will get, you can use associativity now, right?
Yes, ma'am.
Yeah. So because of associativity, just when you start learning groups, you always try to have this thing, like, write it, what is the reason why you are doing it. Okay, so associativity is true. Great. So 1 star E is what? Because E is the identity element, you should get the same element, right? So you have post multiplied by the identity element, so you will get 1 here. Now, yeah, we can resolve this also. What you will get, 1 star 1 is yeah, 1. Oh, sorry, what I did.
Ma'am, this is the same thing.
Yeah, this is the same thing. Wait. What I'm doing, I stuck. Yes, 1 second. 1 star 1. Right. Okay, 1 second.
Ma'am, for 5 and
Okay. Sorry, I should not multiply by identity, because this will give the same thing, right? So yeah, I should multiply. Oh, this is okay. Yeah, 1 second. Yeah, I did a mistake. Don't worry. Like, it's just you need to, what you all have, you just use something from there. So E is the identity element. What you can do, you can actually multiply by the inverse of 1. So I need to do that. So post multiply by the inverse of, sorry, or maybe left, oh sorry, right multiply by inverse of 1. Okay, now what you will get, again use same thing. It's just now you do this. So this is by associativity. Yes. Okay, So here you get this. Now what you can do, 1 inverse is what? This is identity. Is it okay?
Yes, ma'am.
Yeah. So I actually need to do this. 1 inverse again, this is identity. Now this is you. Now you can say 1 identity is 1, and here is this. So these are actually equal. So here we used 1 So basically we used inverse property. Okay. Inverse property, and now here we used identity thing because E is the identity element.
Ma'am, but one more thing.
Yeah.
Does this inverse identity exist for every element or just 1 and 5?
Sorry, no. Here it is given that this is group. So yeah, maybe we don't know which element it is, but we know there is like one of them is inverse of that. Like inverse exists because from the group we know 4 properties. It's closer should be satisfied. Second one is like associativity should be there. Now identity element should be there, and the fourth one is for every
Inverse.
element you should have the inverse. So we don't know which element it is, but we know there is someone, like there is someone for everyone. It's like this, inverse.
Madam,
Yeah.
1 star E is equal to E. How does it? 1 star E is equal to E.
No. 1 E.
How does it imply
No, one
is
star.
equals to E?
Okay. Yeah, sure. So what we did.
Yeah, how does it imply 1?
Right. So you know 1 star
How?
E is what? 1 star E is. Ignore this right now. Just I'm
1.
asking. Yeah, 1. So
Okay.
I just wrote this.
1.
Not from here. Yeah. This is 1, and from here it is E. Right?
Okay.
Okay. So if you have given that something has been multiplied by something, and you get the, like, basically if you have given something, like if it is multiplied by identity and it is giving the same thing, and this whatever it is, so basically what it proves, you could use this one also, like, so this has been given 2 star 1. 2 star 1 is equal to 2. You can also use this by just multiplying by 2 inverse, and you will get the same thing. So basically if you have given one of them, like so basically if I write it a star, let's say whatever it is, and you get simply a for any of a, like for any a, if it is given, then this implies whatever the element here, like let's say this is b, this implies b's identity. So it proves this thing, like it is enough to have with only one element, nothing else. Is it okay? So this is kind of a property. Is it okay? Yes or no?
Yes.
I'm
First,
just
Yes.
first column.
yeah. Sorry. First.
Yes, we got first column right.
Okay, great. Very good. So I'm just spending time on these small things because this is actually group. So it is actually abstraction of numbers, and looks like it's abstraction of numbers, but when it goes beyond that, it will be like you should have all the properties in mind. So better to write it, and better to, like, why I'm writing this here, so that you will understand why this is happening. So just try to write at first, and then later it's good to write every time, so you can always, so just think of it like this. Okay, so from here what we got in this equation, in this table, now you know 1 is the identity element. So 4 star 1 you 1 star 4, you can you know why what it will be, it will be just 4, right? So you have this, actually you know these entries now, because this is just the multiplication with the identity element.
Yes.
Great. Now let's see what are the other things. Okay, so for this,
First
yeah,
row we also got.
yeah, first row we also know. Very good. Yeah. So now let's try to know what are other entries. Okay. Now Okay, it is given that this is an abelian group. We have not used it yet, so let's try to use it and have the things. So second is, okay, it's not a actually property, we will just write because G is abelian. Okay, because G is abelian, what you can do here, sorry, here.
Yes. This will be a symmetric matrix.
Yeah, symmetric matrix. So
So
in the fourth row, like in this row, what you can tell the entries, like which entry you can at least tell me.
uh,
Yes, just think of symmetry as you have said. Which entry
four,
you, yeah,
4 3
4
is
3, yeah,
is
4
one
and yeah, this entry. So
one.
this is 1,
Yes.
very good. So this is
And
coming from, yeah,
5 3
5 3, 5
is
and 3.
3 is
uh,
2.
5 and 3, is it,
Uh,
or anything else?
no, it's not.
Yeah, which one is it? Yeah, you are going in the right direction. It's just this is the and any other entry this is.
3 5 is equal to 5 3. So it
Yeah,
is
yeah, that
2.
is true.
It's
3,
2.
3,
3 5 is 2.
yeah,
Then
yeah, yeah.
5 3 is.
Yeah, so actually I was asking about this row, but yeah, okay, obviously you can write it. Yeah, actually the question is to know this row, so I am actually concerned about this, but that's okay. Okay, why it is symmetric matrix? So okay, don't think of symmetry here, just think of this is abelian group. So in abelian group, what you know, in abelian group you know a star b is equal to b star a. This thing you know, right? So if you see here what will happen, so okay, if you construct like this line, so I'm just trying to make it symmetry, thinking of it in terms of symmetry. So 1 2 should be equal to 2 1, right? A star b should be equal to b a, so this one should be equal to this 1 2 should be equal to okay. So this row elements I will say first and the column elements I will say later. So it's like 1 star 1 is this, 2 star 1 is 2, and here 1 star 2 is 2, so this should be equal. Similarly this should be equal, so like 1 3 should be equal to 3 1, right? And for example, let's say this one, so this is what, this is 3 star 2, so it should be equal to 2 star 3, which is 2 star 3 this entry, so this should be 4. uh, who asked this question? Yeah, Chinari. Yeah, just let me know if you are getting it.
Yes, ma'am.
So it's like symmetry. Why this is happening? Because you know a star b should be equal to b star a. So symmetry means like along this diagonal all the elements should be equal, like that means these should be equal. This element should be equal to this element should be equal to this, like again as I said this is 4, so it should be 4. Is it okay, Janari?
Yes.
Okay, so because of this, as you all were saying, so what will happen? 4 star, 4 star 3, you know. Why? Because 3 is, sorry, yeah, again, like 4 star 3 is 1, this is 1, so 3 star 4 should be 1, right? So this entry should be 1. So we have this one also, so I can write it. Yeah, 3 star, okay, first one is what, okay, so I should write 4 star 3 should be equal to 3 star 4, and okay, better to write, yeah, 4 star 3, the value of 4 3 is 1, so this should be equal to 3 star 4. So why this is happening? Because G is abelian. Okay, now okay, one more entry actually you can find it in this row, because I'm concerned about this last second last row as it has been asked. So can you tell me one more entry actually I can find?
Yes, 4, 5.
Yeah, great. Yes, exactly. 4, 5. So because okay, yeah. 4, 5, this is 3. So 4 is first and like 5 we can say it later, because you can actually say which one is first, but just like be with the notation then. Like 4 star 5 is 3. So 4 star, so 5 star 4 should be 3 also. Very good. So I can write it. So this is 4, yeah, 4 star 5 is given to be, is it 3? So this should be 5 star 4. Okay, very good. Now, because commutative property, so yeah, symmetric relation. Exactly. Okay, now you have two more entries to find. Okay, this is little bit messy. I'm just okay. Okay, tell me now where can I start? I'm just making it little bit clearer. Okay, this is 3, 4, 5, 2, 3, 4, and in this, 1, you know, okay, not required. Here you can, yeah, sorry, which one is it? Yeah, this is 3. Yeah, tell me now, two entries have we need to find now. So, can you tell me how? Can you suggest something here? Feel free to say, don't worry, like, it's okay if you make mistakes. Actually, it's the best way to learn things. Tell me, what can you do here? Like, two entries are missing right now. Okay, a hint is like, yeah, tell me. Yeah, sure.
We can use inverse property. A into A inverse is equal to E.
Right?
We have not used yet.
Yeah, exactly. We have not used it. Can you tell me exactly where can we use it? Like, because inverse, if you see, inverse has been used. So like one, so you don't like, I don't know where to start with that, but yeah, exactly, we can go somewhere. Okay, where one is missing. So yeah, one is missing here.
5.
Yeah, with 5 it is missing. Yeah, you can actually do that. So okay, here is the actually the same thing which I'm going to say now. Actually, it will also be true with the inverse thing. So okay, so there is my, so third, I would say, some claim I'm again writing. Okay, tell me why this is true. In each row, each entry, actually you can write it not just row, you can actually write column also. Each entry, or maybe each element will repeat once, or maybe appear once, and for any finite group. Okay, this is true for just finite group. I'm not saying anything about infinite group, but for finite group we can always see this. Okay, so the claim is, so what does I mean? In any row or column, no entry will repeat. So it's like, it is not like 3 will. So my claim actually is here, if you see in this row 2, this entry will be 5. My claim is this. So basically what I mean, okay, this is again messy. Yeah, so here 2, 3, 4 and 1, so 5 has not appeared, so I'm saying this should be 5. Can you tell me why this is true? So this is my claim. You can also check with this 2 row only. So the
Yes,
claim, yeah, tell me. Yeah.
we got two 4 2, right?
uh, sorry.
5.
Yeah,
We
4.
got hmm,
Yeah,
4
2.
2.
Right. 2. We got 4 star 2 here, but why this is 5? This is my question. So basically I'm asking, do you know why this is true in each row or column? Or maybe you can see in terms of column also, this column, like this column, this column. You can see in column or row, both is fine. Each element will repeat once for any finite field, sorry, finite group. If this is a finite group, each entry will repeat only once. So that is my claim. Can you tell me why this is true? Just try with, let's say with 2. Let's try with this row 2. Okay, so the question really is 2 star any element, let's say 2a, and 2 star, okay, I should write other way around. A star 2 should be, agar, like if this is equal, A star 2 is equal to B star 2, that is exactly we are saying entry means what? Entry means 2 star, sorry, 2 star 2, and let's say this entry 3 star 2. If we are saying these are equal, that means we are saying this, like for some A and B this is true. We actually need to prove that if this is true, like the question really is, if A star C is equal to B star C, then let's say if A B C belongs to G, with this condition, then what actually happens? A is equal to B. So this is actually the mathematical version of this line. So that means if you do this, and not just this, you can this is with row and column, so it's like you can actually take C star A and C star B. So I'm just thinking of like this. So this is actually the statement. Now can you tell me why this is true? Like if you have this, then this. Yeah.
Yes, yes. If we post multiply by C inverse, then A
Exactly.
is equal to B.
Yeah, very good. Yeah, exactly. So A star C, if you post multiply by C inverse, and that exists because this is a group. So this is right multiplication by, multiplication means just operated by C inverse. Okay, and then what you can use? Associativity for both sides. So you will get A star E. So A star E, so this is inverse, so this is just E, and here C star C inverse is E. So you know the reason, C inverse is the inverse of, that is also unique, that's why I'm writing the. So now you know this is identity, you will get A, and this side you will get B. So this is E's identity element. Very good. So this is clear. So the question is like, so because of this, so if you see what does this row means? Row means you are just multiplying, post multiplying by 2. Every element of this has been multiplied by 2. So if you are saying A star 2 is equal to B star 2, for example, if you say 3 star 2 is equal to 4 star 2, that means you are saying 3 is equal to 4, which is not true because these are different elements. Set has been given with this, right? So this should happen. So if this is true, this implies A should be equal to B. So that means any element, so each entry should be different and should appear for finite group. So 2, 3, 4, this element should be 5. Is it clear now? If you have any question, just unmute and speak. Is it clear?
Ma'am,
Yeah.
ma'am, sorry, but would you please repeat for 2 star 4 and how it's 5, ma'am? I just missed out that part,
Okay,
ma'am. Would you?
okay. So,
Yeah.
have you understood this part? Like this condition? I can use color.
Yeah, yeah.
So this is exactly which we are saying. We are saying if you post multiply by the same element, then like if the result like a star c is equal to b star c, then a has to be equal to b. So if you are saying any entry like two, let's say anything like 1 star 2, if you are saying 1 star 2 is equal to, let's say anything like 4 star 2, if you are claiming, so let's say a even. So if you are saying a star 2 is equal to 4 star 2, then so 2 is same, so a should be equal to 4, right, because of this property which we just proved.
Yes, yes, ma'am. Yes,
So
yes.
that means like this element which you have begin with, that is 4, so you are actually saying this is 4. So what does that mean? If you write here 1 or 2 or 3 or 5, that has to be equal to 4. If you are saying the resultant element, like after operation you are getting the same thing, then like if let's say this is 4, you are saying this is 4. Okay, this is 2. Yeah, if you are saying this is 4, that means you are saying 3 star 2 is equal to 4 star 2, and that means 3 is equal to 4, right?
Yeah.
So that is a problem because 3 is not equal to 4.
No.
These are different elements,
Mm.
right?
Yes, ma'am.
Okay, so this has, so if you claim for any element like 1 star 2 is equal to 4 star 2 or 2 star 2 is equal to 4 star 2, you are going in the wrong direction because these elements are not equal, right? So this element should be different from the others, so that is the only option, like 5 is the only option now because 2 3 4 and 1 has already been there.
Okay.
Okay.
Yes, I got it, ma'am.
Okay, great. So yes, so this is yeah, so we have 3 4. Okay, blue is the right option for this. 2 3 4, we got so from here, yeah, 3, we got which one, 1, and now we got here we got 5. So we can write this implies this is 4 star 2. 4 star 2 is equal to 5. Okay, this is something which we got from here. Now using this, actually why I was using this, because you can actually use again this column thing. Now can you tell me which entry this is? This one.
4 star 4 is equal to
Yeah, 4 star
2.
4 is equal to 2, exactly,
2.
because of this column thing. So for column you can always go with like c star a and c star b, so same thing for this. So this implies, and yeah, this implies 4 star 4 is equal to 2. So you got this entry. Now can you tell me the remaining entry, like this entry?
Ma'am, we have 5 left.
yes.
Yeah, 5
It is
left
5.
again. Yeah.
4 cross 2, 5.
Yeah, great. So this implies again, like these are implication to, like these are direct implications because of this third property. So you got sorry, not 4, 2 star 4 is equal to, what was that, 5? Yeah, 5. Okay. So now is it clear?
Ma'am,
Yeah.
union of in this example, union of diagonal element is G. Is
Union.
it true? Union of diagonal element 1 3 5 2 4. Is it true for all abelian group?
Okay, like you are saying these should be different, so we can, okay, don't worry, if we have anything we can always go for proving. So let's try what you are saying. Okay, this color or maybe this color, yeah. So you are saying in general what you are exactly asking, A star A should not be equal to B star B. You are saying this, right?
Yes, yes.
Because diagonal means this. So is it true? A square should not be equal to B square. Okay, square is bad to write. Okay. I don't know, like 2A star A is not equal to B star A. Okay. Does this really happens? Looks like. Here it is true, no doubt, but maybe this is true because it looks like, but for this should be true. If A square is equal to B square, where can we go?
Ma'am, we can start from
Yeah.
A star A is equal to B star B, and then prove that it is a contradiction.
Yeah, that is true, exactly. But now what to do? Like, if you say these are equal, then what can we do? Maybe we can post multiply by A inverse, maybe B star A inverse, and then you will get A, and then let's say you multiply by A inverse.
Yes, we got A is equal to
Sorry?
B.
A equals to B. How?
No.
No, this
No,
is
no.
identity. No, not like this. Let's say, okay, let's say if we are going somewhere from this, because I can't see anything directly, but maybe this is true and maybe not. Oh, sorry, not A inverse. So I'm multiplying by A inverse from right hand side and A inverse from left hand side. So from this and this you get identity, and here A inverse B, or maybe B A inverse. This is abelian. Oh, okay. We have abelianness also. So you get A inverse B square is equal to identity. What from that? I can't see directly. Okay, if this is true, I'll let you know in the next class, or maybe I'll write it in the comment with the proof. I can't see directly, but if I'll check if this is true exactly, then I'll write it in the comment box.
Okay.
Is that okay? Because
Yes.
A square is, I cannot see directly, but maybe this is true, or maybe with abelianness or something. I'm not sure about it. Okay, so I'll write it in the chat box, not chat box, like comment box. Okay, let's see the other question. Suppose AB belongs to an abelian group. So you have some abelian group. Let's say G is that abelian group. Okay, we can change color now. We're using blue. Yeah. So let's say G is that abelian group. Okay. Now AB belongs to G. It is given. E is the identity. Now what is given? It is given that A inverse is equal to B inverse. So this is given. Okay, this is an abelian group. That is important. Just look for what exactly it is given. Okay, again, can you tell me what can we do here? I just think of it what we can do. So this is the property. I can write it clearly. A inverse is equal to B inverse. Yeah.
Yes, ma'am. Since it is abelian,
Yeah.
so we can write AB inverse equal to A inverse B.
Yeah, exactly.
And it's become E.
Right.
B is equal to B inverse.
Exactly. Very good. Yeah, so as you said, yes, exactly. You can actually use associativity. So we use this thing, and then You can write A inverse B because of abelianness. Sorry, this is also associativity. Both are associativity. Or maybe sorry, this is associativity. Whichever you multiply first, like whichever side you start with, doesn't matter. Now here you used abelianness. G is abelian. Now, exactly as you said, now again use associativity. Associativity. You get identity, B inverse, as Shorty said. Yeah, identity is the identity. And here B is equal to B inverse. Sorry, this should be inverse. A inverse is the inverse of A. And here E is the identity. Okay, so you got B is equal to B inverse. Okay, not, this is not enough. What you can do now, like, because you have been asked in these terms, what can you do?
Post multiply with B.
Yeah, exactly. Post multiply by B. Very good. Right, multiply by B. You get B square, and here you get identity. Again, you know, B inverse is the inverse of A of B. Okay. So you got this, and I think that was the requirement. This one is true. Oh, also here, which one is true? As you can actually 4, 5, 1, 2, 3. Okay. Yeah. Is it clear, this question?
Yes, ma'am.
Okay, great. If you have any question, just tell me. Okay, don't worry. Okay, let's read this question. Suppose a group contains elements A and B uh, such that order of A. So order of A is 4. This is the notation of order. And order of B is given to be 3. And A and B belongs to a group. So we are actually in a group thing, and order is actually defined for group. And it is given that, so you have given these two things, and A cube B square is equal to BA. Okay. First, tell me what is the meaning of order. So order of
A power M is equal to, then M is the order.
Sorry, again, can you repeat?
If A power M is equal to P, then
Yeah.
M is the order of A.
Is it true? Something.
In this case, A power 4 is equal to P.
Yeah, that is true. But I'm saying, like, M has one more property, like A raised to power M equals to E. This implies order of M is sorry, order of A is 4.
Smallest value of M.
Sorry.
Smallest value of M.
Yeah, exactly. This should be smallest. So it happens like, because if A square, let's say if A square is equal to E, then A raised to power 4 will again be identity, because you can multiply by A square both sides. So it's like A square multiplied by A square, E multiplied by A square, and that is identity. This is A raised to power 4. So it's like you can square it up. Okay, square means like just operating again the same thing. So this should be smallest. So like, as you can see, it is true for 2, it should be true for 4. So this should be smallest, exactly. So because uniqueness is required, order is again unique. So for uniqueness, you should have this property. This should be smallest. Exactly. Smallest non-negative, yeah, not non-negative, just smallest positive integer. So you have a raised to power 4 is equal to identity, you have b raised to power 3 is equal to identity, and definitely b square will not be identity, or b should not be identity, or similarly for a. Okay, now it is given that a raised to power 3 b square is equal to ba. What you can do to begin with?
Pre-multiply with A and post-multiply with B.
Exactly. You multiply by, so I don't need to. So actually dot is not required. Like this not multiplication. These are operations in between. We are just like by abuse of notation we are not writing it. So a cube, b square, b. We multiplied by a, and b. So left multiply by a and right multiply by b. Actually this is like this. Okay, now because of associativity you will get this. I am okay, this is all associativity. Just understand why these are happening. Okay, so this is a raised to power 4 b3 ab, and actually you can write a square, right? The square is just writing repeatedly. So this is identity, this is identity. So this implies identity is equal to ab square. Okay, so this implies what? Yeah.
Order of AB is equal to 2.
Is equal
Order of
to
AB
or something else?
less than or equal.
Yeah, less than or equal to, exactly, less than or equal to 2. Actually you can actually check this should divide 2 also. So I'm not proving it right now, but it should divide. Like if this is true, something, let's say a raised to power m is equal to identity, this implies order of a should divide m. So this is a property, but we can actually go with less than right now. We don't require it, but you can always check why this is true. You can prove it. Just try to prove everything. Like if you are beginning to do abstraction, you should prove things. Okay, now why this is not 1? This is my question now. Why this is not 1? So let, because less than or equal to means, and this is a positive integer, so order of ab could be 1 or 2. Let's say this is 1. Yeah, so that means ab is equal to identity, right? Because ab raised to power 1 should be identity. That means just ab. Now let's see with the property what we have. Since we have this, that means you can actually write what? Okay, I am just writing in the form. These are not abelian, so don't try to mix things. Just write it in the form, like aq means a, b square means b and b. So here if you see, you can actually do by the associativity, you can multiply anything first. Okay, so you get ab means identity. Now you can again do this. So these are all happening with associativity. This is identity, this is b, this is ba. Now again, sorry, yeah, you can correct me if I'm writing wrong. So ae means a multiplied with identity will be just a, right? You get here b. Now what can you do again this? So associativity and identity property we used. Yeah, tell me.
AB equal to
Just A is equal to A. That
Yeah, exactly. You get a is equal to ba. Now what can you do here?
post
post-multiply with A.
multiply by A
Exactly,
inverse.
very good. Post multiply by a inverse. You get identity, you get identity here, you get b star identity means just b. You actually get b is equal to e. Is this true? Is this true? Like what is given about B?
Yeah.
B is B is something which has order 3. That
Yes,
means
B order 4.
yeah. So B is sorry. What is given? Yeah. B has order 3. That means B cube is equal to 3, and 3 is least. 3 is the smallest in this sense. That means what does that mean? B square cannot be identity. That means B cannot be identity, right? So this is wrong. Are you with me?
Yes, ma'am.
Okay, great.
Yes.
So order of AB cannot be equal to 1. So the only possibility is 2. So we are with the solution. Yeah. So we have answer to be 2. Although 1 was not in the option, but you should know why this is happening. Okay. Is it clear?
And
Yeah.
this can also be done because there is only one identity, and
Yeah.
therefore there is only one element which has order 1. So E, it cannot only be E, so it
Oh, but
cannot be AB.
yeah, exactly. But it could be possible if you multiply A by B and you get identity. These are just notations. So, for example, if I say, let's say A and B are such that which has some property, I don't know, what should I write? Okay. Okay, AB is equal to. Okay, so as in my mind, I can think of like if you are in integers and you get 3 plus 4 plus minus 3. Okay, let's say this minus 5. No, not 5. Okay, I should write it in some other sense. Like in my mind, I can think of some example like this. AC you have, and this is like it should be with both inverse actually. So my point is like if you have 3 plus 4 and here you have minus 7, you get identity, right? So it is possible because here it is happening like this is inverse, but it could be possible that A and B are
Okay.
such that
Minus 3 plus 4.
sorry, yeah.
Yes. Minus 3, if you operate plus 4, then we get 1.
Yeah, here also like something like that. It could be possible that this is A. It could be possible that this whole thing is A. It is possible that anything is possible. Like, so the thing is like these are abstract numbers. Like you don't know what A and B is. So you should have the proof of that because it could happen like A B will give identity because in my mind actually this is happening. This is inverse of A, and because of this actually this should happen. Okay, yeah, actually exactly. So okay, this is not abelian also, no? Yeah. Okay, so basically what I mean, AB is equal to identity. This implies B should be the inverse of A. You can prove this. And now order of so if you know inverse of any element should have the same order. So order of A should be equal to order of B. This will also prove that this is not possible. So these are the properties. So properties, if you know inverse of any element, if why I am saying that, because AB is equal to E. Because of this actually you can prove that B should be the inverse of A. And because of this, if something is inverse of something, then order should be equal. Like order of inverse is also equal. This is true for everything, like not just this case. This is always true. So because of this, order of A should be equal to order of B, and which is not true because it is given to be 4 and 3, and this will So this is not true. So basically, if you are doing things, you should know the reasons. Okay. And as you said, like AB is not identity, but you don't know. AB are abstract things. So A could be 7 and B could be -7. So you will get identity. Are you getting my point?
Yes, yes.
Okay. So this is other proof, like alternate proof. But again, you need to prove these things. So we can go with the first one also. So this is also same. So you can check with this. Okay, great. Okay, let's come to this question. S is given to be the set of all functions f where f is a function. Like this is the set of functions, and sorry, f is a function. So you are familiar with relations and functions, I hope. Yeah. So f is given to be a function. So this is your set. Now S with composition operation. So what is composition operation? We will write it with this composition operation. Okay. So now, okay, so f of g of f means, okay, so this is composition. So we always write like g of f. In that sense we use this o notation. Okay. Let's say these are the things, these are same. Yeah, some drawing problem. Okay, so these are all okay. This is a notation for real number. Okay, so if it is written in this form, like double this, then this is real number set. And if it is written like this is complex number. Z with this, that means integers, and Q with this, yeah, this is rational numbers. So these are notations in mathematics, so you can remember that. So this is the set of real numbers. This is, let's say this is the function f, this is the function g. So composition means if you take any element x, so function is defined on every element. So if you know the image of every element of real number here, then you know the function. Okay. Can you tell me what is the definition of function in terms of like relation and function, if you remember? What is a function? Yeah.
Range must be equal to codomain.
Oh,
This
no,
means
no.
that
That is surjective. Think about it. You are saying like every element should have inverse image. Like if you have any element, there should be some element here. Is that true?
a function what must be
Every element in domain should map with one element in domain.
Yeah. Every element of domain should map to single element, or maybe unique, to unique element of codomain. Sorry, which you said like you were saying range
Yes.
should be equal to codomain. That is
that's
surjective. Yeah, that is the next step. Yeah.
But you are writing unique.
Yeah. Unique.
Okay.
Yeah, unique means it should not happen. If you have any element, it is mapping to two elements. That could happen in a relation, but not in function. Function means every element should map to a unique element. There should not be something and any other relation. It should not be there. It's just one
Ma'am,
element. Yeah.
but if when we solve quadratic equation like then we write x is equal to minus b plus minus square root p, we are actually mapping 2 with 1. Is that incorrect?
Sorry, if you come again.
When we solve quadratic equation, then the solution is x is equal to minus b plus minus under root b square.
Yeah.
But here we are mapping 2 element with.
Oh, no. We are not saying this is a function. We have never said that. We are not actually defining anything there. We're just saying there are two roots. So So there, like,
For this x value we have,
yeah, there are two
matlab,
values.
but we write this.
Uh, have you write it in the terms of functions, like how you are defining the function? What is the domain? What is the codomain?
Okay.
Like we don't have really the thing there. It's just like there is a quadratic equation, you are trying to find the roots, and you have this. Like actually in the roots thing, whichever degree is like it cannot have more than that, and it goes really beyond, like it should be field and everything, like, so that is different thing, so it is not really related to maps. Okay, so here what you have, every element of domain, every element, so it should not be here like if you have 1 2 3 4 5 and just three elements are mapping somewhere. It should happen like all the elements should be mapped. So that is the requirement. Okay, so here let's see what we have now. For so composition means if you have, let's say, x, it is mapping to y, which is unique, and there is something, so like x should map to somewhere, and now you have this z, like some element here, because this is again a function, g is again a function. So the composition means in g of f means first you have applied f and then g. So g of f is x goes to z. So this is your real this is your function, and you can always define it like composition you can do for every element. So so they are asking, so this is actually composition now. So they are asking, is this a, this, if you take s with this composition set, what is this? This is, this a group, is this a commutative group, is this a non-commutative group, or maybe this is not a group like monoid or something. So you need to figure out that. So for that, what you need to do, you always know, you should start with all four properties. Just try to check if not four, five, because commutativity we have also been asked. So let's check. So closer. Okay, you have, let's say, f and g belongs to this set s, so these are functions. Then g of f is what? G of f will again be a function, as we just said. So how can you say like g of f for any element x? You will get g of f of x. This is the definition of composition. So actually I can write it here. G of f of x, any element x, you get g of f of x. Do you have any class? I'll just take 5 more minutes.
Yes, ma'am.
Okay. So g of, okay, that means you don't have any class, right? Yeah. Okay. So x belongs to R. So for any real number, this is the definition of composition. Like you first apply f and then apply g. So that is exactly your function. Sorry, yeah, composition function is this. So you know, because of closure property, for every x belongs to R, so it should belong to S. Because why this should happen? So g of f should belong to S means it should be a function, and that is true. Why? Because if you take any element x, it will map to some element y, and then it will map to some element z, and for every element here you will get some element here. So first property, like every element should be mapped, and second property, it should be unique, because as you can see, this is unique, this part is unique, so this part and this part is unique, so overall thing should be unique, right? So this is really a function. So that was the requirement. Okay. Okay, yeah, this implies g of f should belong to S. Second property, associativity. Sorry, yeah?
Yes, associativity.
Yeah, associativity. Yeah, so for associativity, what can you do? F So let's take three elements of S. That means you have F, G, H belongs to S. This implies H. So what you need to not implies.
F of G of H is equal to F of G.
Yeah. Actually, I'm writing in this sense because we are actually doing F, G, and H. So I'm writing in this form. So this should be equal to show. This should be equal to H of G of F. So this should be equal. What does that mean? That is, so in function, if you define everything over elements, you are done. So think of on element, because actually function is on elements. So you can always think like that for all x belongs to R. This should be true, right? Here domain, codomain are all R real numbers, so we don't have any issue with the other things also, like if it is something else or something. So F and G both are defined over R. Now see, to show this, okay, so let's take the left hand side, H of G of F x. So from the definition, what does that mean? G of F of x, it will give G of fx. First you take F and then this. So we will write it like this, H of G of F x. Right, this is there. So it is from the definition. We have not done anything different. Now this is inside also there is of. So here composition. So here we can write this. And now right hand side, we are just resolving things. Right hand side you have H of G of F, and here you have x. Now let's see, what do you have? Now this is one thing and this is other thing. So H of G and F of x over F of x, exactly what we have. So we have two things and then we do this. So here two things are H of G and F. So H of G, okay, now this is an element. Okay, now this is an element, so this is one thing and this is other thing. So H of G of F, because this is some y, so this is like H of G of y. So this should be equal to H of G of y. So this is y means fx. So this is exactly what I wrote. And if you see, so this implies LHS is equal to RHS, which was the requirement. Is it clear?
Yes.
Okay, great. Yeah, so let's see other thing. So we are done with second property. Now let's come to third, identity. Can you tell me which is identity element?
Yes, f of x is equal to x.
Yeah, exactly. So let's write it, if we can write I, just for the simplicity, like I is identity element. So exactly as you said, take any element, it will map to itself, just mapping to itself. Why this is true? Because if you take f of I of any element x for all x belongs to R, f of, first it will be done I of x, then you will get I of x is x, so you get fx. And other side, if you do I of f of x, this is equal to, now this is the element. Now identity function on this element, because this is just y, some y, I of y is equal to y because it maps to itself. So this is fx. So this is really an identity element. I is the identity element. We don't need to check this is the, because we already know with the group this is true. Sorry, this is not a group right now, so this is unique, you can always check. Okay, now let's come to last thing, fourth, that is inverse. Now can you tell me if inverse exists or not for every element? So f is some function, let's say f belongs to S. Maybe yes or no. Will inverse exist always? Yeah. Just tell me.
Probably no.
Sorry?
Most probably no.
Most probably. Can you think of some example? Simple example if you can give.
For identity, inverse is 1 by x and 1 by 0.
No. Why I
Oh,
didn't.
function.
So these are not inverse means you have like f inverse means if you are going in this direction, f inverse is this. Like if you have any x, if it is mapping to y, then f inverse of y is x. So composition, we are talking about compositions. So here
In many
inverse.
one function, their inverse not is.
Which one?
Some of the
Which one?
many one function, many one.
Many one function, exactly. So if that is many one, can you give me an example? Simple example. Okay, let's take 1, 2, 3. So actually we are in real numbers. Sorry, yeah. So f of x is equal to 1. Let's say 1 for every x belongs to y. So basically
yes, f of
yeah. So minus 1, minus 2, minus 1 by 2, whatever you have, 1, 0, 2, because these are real numbers. So you have everything, root 2. Everything is mapping to 1. Everything is mapping to 1. Now if you try to find the inverse, what you will get? You will get nothing because 1 is like this is not defined. You cannot map anything here. Like 1 has too many images. So what will happen? This is not a function because f inverse is not a function. This is the problem. This is a relation but not a function. Function means every element should be mapped somewhere. Like 2 will not, because there are many reasons. 2 has no inverse image. One of the reason 2 has no image, right? The other thing, 1 has many images, right? So this is not a function. This is a relation but not a function. But S is the set of functions, so this is a problem. So what can you say?
It is a monoid.
Monoid, exactly. So this is a monoid. Okay, great. I hope this is clear. I'll just go last question very quickly. Okay, if you can actually tell me, if you help, I'll do it very fast. So H and K are subgroups. H and K are subgroups of G. This is the notation. Which one of the following is true? So first is H union K is a subgroup or not?
If HK is equal to KH, then H union K is subgroup.
Sorry, if H is equal to K?
If HK is equal to KH, then
Yeah.
H union K is the subgroup.
Okay,
The condition is not.
so that is a condition, right? So this is a condition. So can you so definitely you so you can give an example then, right? So give me an example where H union K is not a subgroup. Like if you are going for the wrong option, then give an example. Yeah, you said it right. H union K is a subgroup if HK is equal to KH. But here that is not the condition. So give me an example. Yeah, Shaurya.
Why is that H union K is equal?
So let's not go to that direction. We will not go there. But just think of, consider any H and K. Just tell me where it will be a problem. Like for example, let's try to prove if it is a group. Okay. So if there is a problem, we will get in the trouble in the process, right? So let's check closure property, right? So in closure, if you take x and y in H union K, then xy, so there could be any operation. So x star y you can write should belong to H union K to show. You need to show if xy belongs to H union K, then H star K should be H union should be in H union K. Will it always be true? I'm saying that
No,
is the
because it's
Yeah.
true when element belongs to H or K, but when elements belong to one belong to H, another belongs to K, it might not be
Yeah,
possible.
exactly. So just think of some example in this case. Because if we are saying something is not true, we should give an example. Yeah. You are going in the right direction. Anyone just try to give an example. Okay, let's take z, integer set with plus. Like so the group is this. So yeah, G is this group, G star is this. Now consider some H, consider some K, and just try to prove H union K is not a subgroup. Like this property exactly. Can you give some example of H and K here? Okay, so I'll just give you.
2z.
Yeah, 2z and K, what you can take?
3z.
3z, exactly. You can take 3z or you can take anything else, but for example, you can take 3z now. So you have 2z and 3z. So x and y, what can I take? Take something. So for example, just take 2 in H and 3 in K. You know this is true since. So this implies 2 and 3 will belong to H union K. As you said, one should belong to H and one should belong to K. Then we
Yes,
can.
yes,
Yeah.
5 does not belong. Okay.
Yeah, now 5. So if you take 2 plus 3, the closure property, then 5 will not belong to H union K. Then there is a problem. So exactly as you said, one should belong to one and other should belong to the other one, then you will get in trouble. Great. So this is a counter example. So H union K is not something which we need. Now think of H intersection K. Okay, I'll just go with the 3 first, because if you know H intersection K is the right answer, but let's think of H bar. H bar is actually the set of like G minus H. Okay, so this is a notation, like this is not this. Okay, so all the elements G such that G belongs to G and G does not belong to H. So it's like if G is this and H is this, then this is the part is H bar. Okay, so this is H bar means. So can you tell me why H bar is not a subgroup? Simple property problem. H bar, you understood? What does that like? What is H
Yes,
bar?
yes, complement.
Yeah, complement of H, exactly. Um, just think of closure, associativity, identity, and inverse. One of them, if you can uh, prove it, it is not true, then we are done. Yeah. Yeah, Chennai.
Sometimes identity element.
Yeah, exactly. So if identity belongs to H, you know that because H is a subgroup. Since H is a subgroup, yeah, H is a subgroup. This implies identity belongs to not one. We should write E. E belongs to H. This implies E does not belong to H bar, and that is a problem. This implies H bar is not a subgroup, because identity is only one, because we are in the group big group G. Okay, and big group G has one identity. So identity is unique. G has one identity. So if H has it, then H bar does not have, and that is a problem. Okay. Now come to the second one. As I said, H intersection K is your right answer. Let's check it. So first thing, closure. Closure means, let's say X and Y belong, yeah, X and Y belongs to H intersection K. This implies XY belongs to H and XY belongs to K. This implies, now you know X and Y both belong to H. That means X star Y will belong to H, and also other side X star Y will belong to K because of these properties. Now you have X star Y belongs to H intersection K because it belongs to both. Then we are done. Closure done. Associativity.
Since XY,
Yeah.
XYZ all belongs to either Z or K, then
Exactly.
associativity is inherited from them.
Yeah, exactly. So if X, Y, Z belongs to HK, this implies, actually you can go with G also, like X, Y, Z belongs to G also. This implies, and there it holds G is a group. Then we are done. Since G is a group, this implies associativity holds here. Okay, exactly, inherited from G, exactly. uh, Third one, identity. Now tell me about identity. So let's say E is the identity element which definitely belong to H and K, right? So sorry, yeah, if E is the identity element of G, then E belongs to H and E belongs to G because these are subgroups. H and K are subgroups, so they are itself groups. So this implies E belongs to H intersection K. So identity is there. Now inverse, that is also, I hope you agree, because if XY belongs to H intersection, sorry, not Y. So if X belongs to H intersection K, this implies X belongs to H and X belongs to K. This implies X inverse belongs to H because inverse exists, and X inverse belongs to K, and this implies X inverse belongs to H intersection K. And we are done. Always think, because we are in the bigger group, so inverse is the same inverse. So H and K are the subgroups of G. So inverse is unique. So it is not like there are two inverse. So inverse of X in H is different, or inverse of X in K is different. That cannot be possible. That's why we are in the good condition. So H intersection K is a subgroup. And we are done. And we are done for today also. So this was the last question. If you have any doubt, just let me know.